Okay. Let's pray. Dear Heavenly Father, thank you for another session, another week that we can study about the beauty of your universe, which mathematics in a way reflects that, as you have created this universe with some mathematical pattern and beauty. Help us to appreciate that, help us to recognize that and give glory and honor to you. I ask your blessing upon all these dear students. I especially pray for Brother Richard that you keep him healthy. Don't let him to catch a cold or come down with a cold or flu. And bless all of the dear students, also Brother Ruben. Help them in doing their homework, assignment, learning, and take away from them fear and anxiety. In Jesus' mighty name we pray. Amen.
Amen.
Good. Well, I put the answer. Hello, brother.
Hey, Brother
Good to see you. We just prayed. I put the answer for both the quiz 1 and assignment 3. I opened it under the lesson 3, session 3 for today. You can see that. But there are a couple of things I wanted to go over. Just let me just go to share screen. And yeah, we are recording. So, where is it? Okay. I believe you can see this. Okay. One more. Couple of things. You all did very good, but just a few things. Number 5, when it says set of X, such as X is a lowercase letter of the alphabet that follows D and comes before J. So it doesn't include D and J, would be E, F, G, H, I. On number 8, when it says a set of X, such as X is a natural number, and it's less than and equal to 4, so you have to have 4 in that set. Would be 1, 2, 3, and 4, because that sign, when you see that sign, the sign here, with this little thing down there, means equal, so it includes 4. So you have to have 4 also in your answer. Question number 10. Most of you did good. Just one little thing. Brother Ruben, just you see, if you notice, when it's asked for, there's a little sign at the top of the final parenthesis. So number 10. So if it gives you the universal set, our universal set is
1, 2, 3,
A, B, C, D, and E. D and E. Okay, that's our universal set, and then it asks for. Notice it asks for intersection of not A and B, but then it puts another parenthesis and asks for then not whatever comes there. So not A, well, in our A is the set A is B and C. B is B, C, and E. So when we want to find not A, let me make sure I'm at the right place. Okay, not A, whatever which is not A, but it's part of the universal set. Well, A contains B and C. So not A would be A. We don't include B. We don't include C, and D and E. Okay. Then intersection of that with B. Well, B here is B, C, and E. What's common between B, C, and E is only E. See that? Okay. So intersection of not A and B would be E. But remember, we are asking for whatever that set is, make it not. So not E. So it means take whatever is in the universal set A, B, C, and D, and that's the answer. You follow me?
This is for 10, right?
That's for number 10. Yeah.
Okay.
All right. Okay. Let me then clean here. On number 11, there's a number 11. No, I'm sorry. Yeah, you all did good on number 11. Number 12, just one thing, remember, Richard, especially you on number 11, when you see those signs, you have to add them. So when we have these little sign which looks like this, and it says this is equal to 1 in our numerical system, and then you have, on the first example, you have 5 of those things, so you have 1 plus 1 plus 1 plus 1 and plus 1, which makes it 5.
Okay.
You don't just put 1, but add them.
Okay.
The second one, we have this sign which is, sorry, my drawing is not very good, which means 10. So we have 10 plus 1 plus 1, which is 12. And for the third answer, remember, these are all together. You have 4 of these symbols you have 4 of these. So you add 10 plus 10 plus 10 plus 10. And then you have 5 of these ones. Oops. 5 of these ones. Sorry about that. So you add, okay, 1 plus 1 plus 1 plus 1. So you get 45. All right?
So that's all one one number that
Yeah, it's exactly. It's all one number.
First we add the first line, then we add the second line, then add both of them together.
Yeah. It becomes 45. Okay? These were the common mistakes, but you did good in the rest of them. Any questions you have? I guess not. So let's continue for now. And for the quiz one, it's just a matching. You just have to know the definitions and look at the answer. I opened the answer for you under lesson 1. You can see your mistakes and learn the proper definition for each of those questions on the first column, and you find the answer on the second column. All right. So let's go just take a look at our syllabus briefly.
For our PowerPoint, it should be taken out of
nickels.
Out of nickels.
One of the chapter. Pick one of the chapter that you like and then just let me know if just based on, just let me know which chapter you have chosen. And remember, prepare a PowerPoint. I put an example for you, and you will share your PowerPoint at the last class session. And only about 10 minutes, just 10 minutes, not more than that. Okay, so remember the PowerPoint. We are going to look at chapter 5. We worked with the number, rational number, the relationship, decimal, fractions, percentages, and ratios. For this week, start working on your PowerPoint. Read chapter 4 of Nichols and then submit the reading summary as you have done so far. And take quiz number 2 by Sunday, due Sunday before the midnight. Okay, so let's go to our PowerPoint. Okay. You all can see that, I believe. Okay.
Yes.
Okay, we are going to talk about numbers, number theory, and number theory, excuse me, is the study of numbers and their properties. Numbers we use to count are called counting numbers or natural numbers. Because we usually begin counting by number 1, the set of natural numbers begins with 1, and this is how we denote it. It's n equal those parentheses 1, 2, 3, 4, 5. Oh, one more thing. When you put a set between the elements of the set, just put comma. Don't put the word and. Just put the comma. Okay. Any natural number can be expressed as a product of 2 or more natural number, and that means they're known as factors of that natural number. For example, 8 is a product of 2 times 4, or it can be 8 times 1. 16 is a product of 14 times 4. 19 times 1. And 19 is a prime number for that. We will get to it because of that. Numbers 1, 2, 3, 6, and 9, and 18. I'm sorry. Okay. 1, 2, 3, 6, and 9, and 18. They are all factors of 18. That means each of these numbers divide 18 without a remainder. We show divisibility. We say if A and B are natural number, we say that A is a divisor of B, or A is divisible by B, or A divides B, and we symbolize it like that. A, then you have one vertical line, B. I'm sorry. Okay. For example, we say if A divides B, then B is divisible by A. And that's the way how we write it. B is divisible by A. A can divide B. If 4 divides, example, 4 divides number 12. So we symbolize it by this, 4, horizontal line, 12. Because the quotient of 12 divided by 4 has no remainder. Note, every factor of a natural number is also divisor of that natural number. And don't confuse these symbols. Don't confuse the symbol that we have a vertical line B and a dash B, or A divided by B. Okay. Every natural number greater than 1 can be classified either as a prime number or composite number. So we have prime numbers and composite number. A prime number is a natural number greater than one that has exactly two factors or two divisor, either itself or one. Composite number is a natural number that is divisible by a number other than itself and one. And number one is just considered a unit. It's neither prime nor composite. So, for example, if I ask you like find all the prime numbers less than 100, that's the way that's how you do it. You cross out one because that's not a prime number. You circle number two, and I will show you a table. Then you that's your first prime number. Two can be only divided by itself and one. Then you cross out all of its multiples, 4, 6, 8, up to 100. And you do the same with 3. Then we go to 5. Then we go to 7. We do all of that. Then our charts looks like this. It becomes like that. We crossed 1 because 1 is not a prime. Then 2. We crossed all the factors of 2 from all the way 4, 6, all the way to 100. Then we came to 5. We circled 5, but we crossed all the other multiples of 5. Then we came to 7, and we did the same thing all the way. So that's all the prime numbers from 1 to 100. And so this method is repeatedly marking things as a composite. The multiple of each prime number was a method that invented by a Greek mathematician, Eratosthenes from the 3rd century BC. Then here we come. Now, I will show you, you may get kind of confused about all these definitions, but once we get to examples and actually doing it, you will see it's very easy. Each composite number can be expressed as a unique product of prime numbers, and that's where we will have factor tree. We use factor tree to find prime factorization of a composite number. And to find the prime factorization of a number, we select any two numbers whose product is the number to be factored, and then we keep going on. If the factors are not prime, we continue till the result of what we have. They are all prime numbers. For example, look at here. If we start 210, well, that's a composite number, definitely, because it can be divided by itself, it can be divided by 1, and it can be divided by 2, it can be divided by 5, a number of other things. So we start with 2. We say it can be divided by 2. It can be a product of the 2 and 105. You multiply 2 by 105, you get 210. All right? So this is prime. The 2 is prime. So we leave that alone, we come to 105. But 105 is not a prime. It's a composite number. We can still break it down. It can be the product of number 3 and 35. If you multiply 3 by 35, you get 105. 3 is prime, so we leave that alone, we come to 35. 35 is a product of 5 times 7. Now, all of them, these are all prime. So we stop right here. So we get these prime number, 2, 3, 5, and 7. And if you multiply these things by each other, you get 210. Or you can do 210 with, instead of starting with 2 and 105, it can be the product of 14 and 15. And 14 times 15 gives you 210. And 14 can be, again, breaks down, you can break it further down to 2 and 7, and 15 to 3 and 5. The final result are the same. You have 2, 7, 5, 3. You have 2, 7, 5, and 3 here. This is called factorization tree. You branch it down all the way till you get the all the prime number. Okay, and if the thing is, if you multiply this prime number together, you get the original number. 2 times 7 is 14. If you multiply 14 by 5, it's 90. 90 times, no, I'm saying 70. 70 times 3 is 210. All right. Now you will see the benefit of this later on. You can do prime factorization also by division. Let's say we have this big number, 34,200. We divide it by 2, we get 17,100. Again, divided by 2, we get 8,550. We divide it by 2, we get 4275. Remember, we use a divisibility test, or just remember, a number is divisible by 3 if the sum of its digit is a multiple of 3. This here is 4 plus 2 is 6. 6 plus 7 is 13. 13 plus 5 is 18. And 18 divided by 3 is 6. So we keep doing that, and then we come here, and also about 5. A number is divisible by 5 if its last digit is either 0 or 5. So we can divide it by 5. So these are the prime number. And we stop right here. 19 is prime. If you multiply these blue number, you get the original number, 34,200. All right? We continue. Now, one of the very important thing in math is finding the GCD, the greatest common divisor. The greatest common divisor, or GCD, is a set of natural number. Of a set of natural number is the largest natural number that divides without a remainder every number in that set. For example, if we want to find the what's the GCD of 12 and 18? Well, 12 can be written, if you write it as a set, what are the number that is divisor of 12? You can have 1, 2, 3, 4, 6, and 12. 12 can be divided by these numbers, and there's no remainder. 18 can be divided by these number, and there is no remainder. You find the common numbers between them, and I put them as bold for you. The common divisor are 1, 2, 3, and 6. The greatest common divisor is 6. That means the greatest number that you can go and divides both number 12 and number 18, and there is no remainder, is 6. Okay? All right. Let's continue. We can, let's say we want to find the GCD of 2 or more numbers. We find their prime factorization for each of them, list each common prime factor with the smallest exponent that appears in each prime factorization. Then we find the product of the factors we find in step 2. Let me see. Okay. Let's do an example. Let's look at page 232 and 233.
Did you say page 233?
Yeah, 232 and 233. For example, on page 232, it asks find the greatest common divisor for 216 and 234. We use the prime factorization tree for each of them. 216 can be factored as 2 times 108, then 108 can be 2 times 54, and we continue till we come to 9. 9 is a product of 3 times 3, then we stop there. These are all prime number, those in gray bubble that you have in your textbook. And we do the same thing with 234. We get the primes 2, 3, 3, and 13. So notice we write 216 is equal to 2 times to power of 3, because we have 3, 2, okay? Times 3 to power of 3. You follow me? And 234 has 2 times 3 to power of 2, because we have 2, 3, and times 13. Then we find the prime number prime numbers that are common between each. Select each prime factor with in fact, no. We select each prime factor with the smallest exponent that is common to each of them. So we have, you see, we have 216 and 234. Let's see, the common, the 2 prime numbers common to both of the factorization is 2 and 3, and we therefore the exponent associated with 3 in the factorization are 2 and 3. We select 2, the smallest one. Therefore, it's either 3 to power of 2 or 2 to power of 1. These are the GCD of these two numbers. Or you look at example number 4 on page 233. We do the same for 40 and 24. We find the prime numbers. 40 can be written as 2 to power of 3 times 5. 24 as 2 to power of 3 times 3. The greatest common divisor between both of them is number 2, and the exponent, the least exponent, is 3. So the GCD is 2 to power of 3, or 8. Okay.
I have a quick question.
Sure.
So like on that example on 40 and on 24, it says 40 equals 2 to the power of 3 times 5. Do we always put, like, for example, since I get it 2 times 2 times 2, do we always put that before the single digit? Like how it says 2 to the power of 3 times 5, or would it be the same thing if it was 5 times 2 to the power of 3?
It doesn't matter. Okay. It's just easier to start with the lower number and then you go to the higher number. It's easier to start with the exponent and but it doesn't matter.
It comes out to the same. Okay.
Okay. So this is called greatest common divisor. And the question was, for example, for an intramural league, you need to divide 40 men and 24 women into all males and all females teams so that each team has the same number of people. What is the largest number of people that can be placed on a team? And the largest number of person that you can have in a team is 8. That's the greatest common divisor. Okay? Now, let's go. There's another thing. It's called least common multiple. The least common multiple, or LCM, of a set of natural number is the smallest natural number that is divisible without a remainder by each element of that set. For example, if we want to find the least common multiple between 12 and 18, in the past example, we look at the greatest common divisor. Now we want to find the least common multiple. Again, we write the multiples of 12, 12 times 1, 12 times 2, 24, 36. It goes on and can go on all the way, and that's the way we have these three dots. For 18 is 18, 36. We do the same thing. We go up to 144, and then the three dots. Some common multiples of 12 and 18 are 36, 72, 108, and 144. The least, the smallest common multiple is 36. In other words, the smallest number that you can use, that can be the multiple of 12 and 18 is 36. 12 times 3 and 18 times 2, they are both 36. You cannot get smaller than that. You follow? All right. In the examples, you will see how these are working. Okay, are you guys okay? All right, that's cool. Okay, now we want to find the common multiple of the two or more numbers. Again, we use prime factorization. We list each prime factor with the greatest exponent that appears in any of the prime factorization. Then we find the product of the factors in step 2, and that's how we find our answer. Let's look at page 234 and 235. In example 5 on page 234, it says find the least common multiple of 144 and 300. First, we do the prime factorization. 144, when you do the prime factorization, you will find the final result is 2 to the power of 4 times 3 to the power of 2. For 300 is 2 to the power of 2, 3 to the power of 1, and 5 to the power of 2. Step 2, we select every prime factor that occurs, raised to the greatest power to which it occurs in this factorization. So the prime factors occurs are 2, 3, and 5, and the greatest exponent that appears on 2 is 4, so we choose 2 to the power of 4. The greatest exponent for 3 is 2, so we choose 3 to the power of 2, and the greatest exponent for 5 is 5 to the power of 2. So we've chosen 2 to the power of 4, 3 to the power of 2, and 5 to the power of 2. Then we do the multiplication. On page 235, you can see that 2 to the power of 4 times 3 to the power of 2 and times 5 to the power of 2. You got 16 times 9 times 25, you get 3,600. So the least common multiple of 144 and 300 is 3,600. The smallest natural number that is divisible by both 144 and 300 is 3,600. Okay?
So, Professor, so when you when you saying, okay, 144 equals, so is that 2 times 4 times 3 times 2?
3 to the power of 2.
3 to the power of 2.
Yeah. So it means if you multiply 2 4 times, and if you multiply 3 2 times, and then multiply the result of these two by each other, the answer is you get 144.
44. Okay. Okay.
All right. Let's look at example number 6. It says a movie theater runs its film continuously. One movie runs for 80 minutes and a second one runs for 120 minutes. If both movies begin at 4 p.m., when will the movies begin again at the same time? Okay, the shorter movie lasts 80 minutes or 1 hour and 20 minutes. It begins at 4, so it will be shown again at 5:20. The longer movie lasts 120 minutes or 2 hours. If it begins at 4, it will be shown again at 6. We are asked to find when the movies will begin again at the same time. Therefore, we are looking for the least common multiple of 80 and 120. So we want to find the least common multiple of 80 and 20. Okay, again, we do factorization. 80 is equal 2 to power of 4 times 5 to power of 1. 120 is equal 2 to power of 3 times 3 to power of 1 and 5 to power of 1. We do that by factorization. The least common multiple, we choose all the primes, 2, 3, and 5, and then we pick the greatest exponent. For 2 is 4, for 3 is 1, and for 5 is 1. Multiply them together, the answer is 240. It means it will take 240 minutes or 4 hours for the movie to begin again. If the movies started at 4 p.m., they will start again together at 8 p.m. All right. Okay. Let's continue. Okay, now this is easier, so you can relax a little. We come to integers. Integers are fun and they're very easy. When you add 2 positive integers, you get positive integer. If you have 2 negative integers, if you add them, you get a negative integer. If you have a 2 integer that the positive one is bigger, the negative one is smaller, the answer would be positive. And same is other way around. If the integer, the largest integer is negative, and you add it to a positive integer, you get a negative integer. I will show you example. Don't get confused. Don't worry. Through example, it became much easier. If you multiply 2 positive numbers, you get a positive number. If you multiply 2 negative numbers, you get a positive number. But if you multiply mixed positive or negative, negative or positive, you always get negative. When we talk about integer, think about the number line. You have 0 as the set as a beginning, and then all the numbers, all the numbers to the right of 0 are positive, to the left of 0 are negative. So when we have +4 and -4, they are opposite of each other. This helps you to visualize the integers on a number line. These are set of integers. For example, we use this sign for less than and this sign for greater. If I have -4 and 3, which one is bigger? Tell me.
The 3.
3, yeah. 3 is here. If I have -1 and -5, which one is bigger?
-1.
-1, because -1 is here and -5 is here. If I have -5 and -2, which one is bigger?
-2.
-2. If I have 0 and -3, which one is bigger?
0.
0.
Yeah.
So based upon that, you either put a less than or equal. All right. The absolute value of an integer, we call it A, we put it in there, and we put 2 vertical line around it, is the distance from 0 to that number. And because the absolute value describes a distance, it can never be negative. For example, if I ask you what's the absolute value of -4 is 4. It just shows the distance of that number to 0. If I ask what's the absolute value of positive 4, what is the absolute value of positive 4? Again, it's 4, because that only shows the distance between that number and 0.
Question.
Uh-huh.
If you had a -4 and a +4, what would it be? 0 because it's both of them are the same number?
It depends on what I'm going to do with them. If I'm adding them together, +4, +4 added to -4, the answer is 0.
0.
But it depends what you do. If I multiply them, the answer will be -16. 4 times 4, 16.
16.
Plus
Okay.
times negative becomes negative.
Okay.
Okay.
Mhm.
Now, rules for addition of integer. I just talked about that. Add their absolute value. The sign of the sum is the same as the sign of the two numbers. Subtract the smaller absolute value. If the integers have different sign, subtract a smaller one, a smaller absolute value from the larger absolute value. The sign of the sum is the same as the sign of the number with a larger absolute value. And we can also add a two-digit number results in regrouping. We can do borrowing. Let me show you example. For example, if you have here -3 plus -2, 3 plus 2 is 5. These are both negative, so you get -5. So it means if I'm here -3, I go 2 units again toward the left, I come to -5. All right? Good. If I have -1 plus -8, what would be the answer?
-9.
-9, exactly. You just add their absolute value, 1 plus 8, 9. They have the same sign, so you just put the sign negative there. In other words, you are here and you want to continue 8 more units toward left, you end up okay. For multiplication, as I mentioned, if they are the same sign, a positive plus times plus is plus, negative times negative is plus. If they are mixed in any way, the answer is always negative. Exponent indicates repeated multiplication. So rules for multiplying real numbers can be used to find exponential expression. Let's go to page 244 one more time. Okay. For example, look at page 244, example number 6. In fact, let me show it to you by that. In fact, that would be an interesting, interesting thing to do with this, my tablet. Just so, let me come out here. Number. Okay, let me go to another share screen, which is here. Okay. Let me. All right. So the first one, for example, it says if you have a -6 and then parentheses to power of 2, what would be the answer? So that means -6 times -6. Okay? And then that minus times minus is plus. 6 times 6 is 36. Okay? But look at number B. In number B, it asks what's the answer for if I have minus 6 to power of 2. There is no parentheses. You see, in the first one, this 2 applies to both 6 and to also the sign. But here, the 2 only applies to 6. So this is equal to minus 6 times 6 equal to minus 36. So you see the difference? Just having that parenthesis makes that difference. Or look at example C. If I have minus print, I have parentheses. Oops. Minus 5 to power of 3. Okay? So this 3 applies to both the sign and also the number. It means minus 5 times minus 5 times minus 5. Negative times negative, positive. Positive times negative is negative. Do you follow me? Oops, let me do this better. So negative times negative is positive, positive times negative is negative. Okay, do you follow me?
Yes, I'm following.
Okay.
I'm kind of lost. I'm kind of lost right
Okay. Here, I have one negative times negative times negatives is plus. Minus 5 times minus 5 is plus 25. Okay?
Okay, so 5 times 5 is 25.
And the negative times negative is plus. Okay?
Yes.
Then I have minus 5 here. Plus times negative, what's the answer?
Negative.
Negative. 25 times 5 is 125. You follow?
Yes, yes.
Okay, so you just have to keep in mind these, where is that exponent? Does it apply to the both sign and the digit or only to the digit? You got to just be careful about that. All right. So let's go back to our.
The ones that didn't have parentheses around it, that with that
the exponent only applies if it doesn't have a parenthesis. The exponent only applies to that number.
the number, okay.
But if there's a parenthesis, the exponent applies to both the number and the sign.
Okay, yes, okay.
Okay.
Mm-hmm.
So evaluating exponential expression, we talked about that. Now let's look at this one. Rules for dividing is the same as rules for multiplication. Again, if you have both of them positive, you divide them together, you get positive. If both of them are negative, still you get positive. But if they are mixed, you always get negative. All right. So let's continue. We come to the order of operation. This is number 26. Let me go there. Okay. All right. So order of operation. This is important. Lots of time people make mistake on the order of operation. We perform all the operation within the grouping symbol, parentheses. We evaluate exponential expression. Then we do multiplication and division, and we work from left to right. and then we do addition and subtraction in order with which they appear, again, working from left to right. So you have parentheses, exponent, multiply, divide, add, and subtract from left to right. Let's look at 246 and 247. Okay. For example, on 246, example 7 says simplify 6 to power of 2 minus 24 plus divided by 2 to power of 2 times 3 plus 1. So we write it, then we take care of first, we do the exponential expression. 6 to power of 2 is 36. 2 to power of 2 is 4, okay? So I write it again. You see that in the second line. 36 minus 24 divided by 4 times 3 plus 1. Then we perform multiplication and division from left to right. The first one that I see is a division. 24 divided by 4 is 6 times 3 plus 1. Then again, the next operation is multiplication from left to right. 6 times 3 is 18. So I get 36 minus 18 plus 1. And when you do addition and subtraction, you get 19. All right. Or let's look at example number 8 on page 247. It says simplify minus 6 to power of 2 minus parentheses 5 minus 7 to power of 2 times parentheses minus 3. Okay, I write that thing. Then I first want to, I work from inside the parentheses. Inside the parentheses, what I see is 5 minus 7 becomes minus 2. So I have minus 6 to power of 2 minus parentheses minus 2 power of 2 times minus 3. Then I take care of the exponent. Minus 6 to power, parentheses to power of 2 is 36. Remember, you have the parentheses and you have a 2. The 2 applies to both the number and the sign. And then minus 2 to power of 2 is plus 4. So I can just bring it out. So you have 36 minus 4 times minus 3. 4 times minus 3 is minus 12. So I have 36 minus minus 12. Minus times parentheses minus 12. So minus times minus becomes positive. I have 36 plus 12, or the final answer is 48. Do you follow? If you have any question, please feel free to ask.
Can you work that again?
Okay. Yeah, let me maybe, in fact, I use my tab.
Real quick question. So on that
Sure.
last part right there, where it's 36 minus, and then you have the parentheses minus 12, it's not 36 times 12 because it's in the parentheses.
No, it means there's a 1, but we don't write a 1 because it doesn't make any difference. So it's that negative sign times the parentheses minus 12. So it makes it plus 12. So you get 36 plus 12. Okay. So if I want to do that, let me on the tablet. Where is the tablet here? And I clean that up. Okay. All right. So we want to simplify this expression, which is minus 6 to power of 2 minus 5 minus 7 to power of 2 then times minus 3 to power of 1. Actually, we don't write it. So we always start from, we do in whatever we have to do inside the parentheses. So we start from here. We take care of this. 5 minus 7 is minus 2. So I put that there, to power of 2 times minus 3 here. And I have also minus 6 to power of 2. Okay? Then I take care of the exponent. Here, this 2 is outside the parentheses, so applies to both the sign and the number. So minus 6 times minus 6 is plus 36. All right? You follow me? Richard, are you okay? Okay.
For that, for the, because you know how you said you always start in the middle and work your way out.
Oh, it doesn't matter. No. You start from that because of the parentheses, but we always start from left to right.
Oh, gotcha.
Okay.
You always start with the parentheses, basically, regardless of where it's at.
Yeah, and then here is minus 2 to power of 2. Minus 2 times minus 2 is again plus 4. And then times minus 3. Okay? So I got 36. Here, minus times plus is minus. That becomes minus 4 times minus 3. I might did I write it right? Yeah. Okay. And then here, I get 36 minus times minus. What's the answer? Plus.
7.
No. Minus times minus is plus. 4 times 3 is 12. Okay. So the final answer is 48.
Okay.
So we start. Let me see. Let me use maybe another color. We start with parentheses. We take care of inside the parentheses. We get minus 2. Then we go from left to right. And we take care of the exponent. And then, we keep in mind plus times. If you have plus times negative is negative. If you have negative times negative is plus. And we keep that in mind. And we do all the multiplication, addition, and we get 48. That's the final answer. All right? Okay. Let's move on. So let me go to the PowerPoint. Okay. So the order of operation. First parenthesis, no matter where it is. Then exponent, multiply, divide, add, and subtract, but you do those from left to right. There is this kind of phrase, please excuse my dear Aunt Sally, P for parentheses, E for excuse for exponent, my dear, multiplication and division, and Sally, addition and subtraction. From first we do the parentheses, then everything else we go from left to right. Rational number, the set of rational numbers, we put a symbol Q, is the set of all the numbers of the form that P can be divided Q, where P and Q are integer and Q is not 0. You cannot divide by 0. And every rational number, when it's expressed as a decimal number, will be either a terminating or repeating the decimal number, like a pi. For example, these are fundamental laws for rational number. If A is A divided by B, A can be is a number when C is not a 0, so you have A over A, if you have A over B is the same as if you multiply the numerator and denominator by number C, which is not 0, the answer is the same. A divided by B is the same as AC over BC. 1 over 2, if you multiply here, both the numerator and denominator by any number, by let's say by 2, you get the same number, 2 over 4. 2 over 4 is the same as 1 over 2, okay? And here you can see the visualization. This is 1 over 2, 1/2. The orange side is a half of the circle. Now, if I divide the circle to 4 parts and I pick 2 parts, again, the answer is the same. All right? So now we have what is called proper fractions, and I'm sorry, this is, I have a hard time seeing this. Oops, what happened? Okay, we have mixed number and improper fraction, converting mixed numbers to improper fractions. Let me try that. I hope don't. Oops. Okay. If we multiply the denominator and of the fraction in the fixed number by the integer preceding it, add the product you obtain in step 1 to the numerator of the fraction in the mixed number, the sum is the numerator of the improper fraction, and the denominator of the improper fraction you're seeking is the same. Again, let me show you through example. That is much easier to understand. Let's go to page 252. Let's go to page 252 and look at example number 2. We want to convert 3/4 to an improper fraction. The number 3/4 is called a mixed number. We want to make it into an improper fraction. So what you do, you take the 5 in the denominator, multiply it by 3, by that digit, that integer next to the fraction, and then you add that to the numerator. So 5 times 3, 15, plus 4 is 19. The final, the denominator still remains the same. So 3/4 is the same as 19 over 5. It's just that the first one is called the mixed number, the second one is called improper fraction. Or if you look at the example under it, it has -2 3/4. That's the mixed number. We want to make the improper fraction. You multiply 4, the denominator, by the number, 4 times 2. You keep the sign where it is, that negative number. And then you add 3, becomes 4 times 2, 8, plus 3, 11. So it's 11 over 4, and then you keep that negative number. All right. We can mix number. I have examples here. For example, if I have 2 1/4, basically, if you want to visualize it, it's like 2 yellow circle and 1 circle, which only 1/4 of it is yellow. So you have 2 1/4. You write it this way. Is the same as if I multiply 4 by 2, 8 plus 1, 9. Is the same as that. Because if I have 3 circles and I divide each of them to 4 parts and I pick 9 of them, you see even in a visualization, you can see that they are the same. All right. Converting improper fraction to mixed number, you divide the numerator by the denominator, you identify the quotient and the remainder. The quotient that you find in step 1 is the integer part of the mixed number. The remainder becomes the numerator. Again, through example, it's much easier to see that. If I have 7/4, that's improper fraction. Then you divide 7 by 4. 4 goes to 7 one time. The remainder is 3. The remainder becomes the numerator. The denominator remains the same. The quotient 1 becomes that integer, the whole number right here.
Know how to start six, not there.
So let's look at, for example, page 252, 253. Like on page 252, you have, it says convert, example 3, convert 42/5 to a mixed number. So you divide 42 by 5, 5 goes to 42 8 times. So you have the quotient 8, remainder is 2. So you write, you see the denominator is still the same. The quotient becomes the integer, so it becomes 8, and the remainder becomes the numerator. So 42/5 is same as 8/5. Or if you want to convert 29 minus 29/8 to a mixed number, you divide 29 by 8. 8 goes to 29 3 times. You have quotient 3, that becomes your digit. The denominator remains the same. The remainder becomes your numerator. All right. Okay.
And in that specific case, we're keeping the negative sign, right? Because it's negative.
Oh, yeah.
Gotcha. Okay.
Okay. Multiplication of fraction is simple. Again, when you just multiply the numerator and denominator. If I want to multiply 2/5 by 3/4, you multiply 2 times 3, 6, and 5 times 4, 2. So 6/20 is your answer. You can simplify it and becomes 6 divided by 2, it becomes 3. 20 divided by 2, it becomes 10. Okay? You can, if when you multiply or divide the numerator and denominator of a fraction, you are not changing its value. So you can do that by same number. Let me emphasize that. Or when we want, let's say we have fractions we want to divide. The only thing that you need to remember, in a division, you just invert the second fraction. 4/5 divided by 2/3 is the same as 4/5 times 3/2. I just inverted the second fraction. And then you multiply the numerator, 4 times 3, 12, and the denominator, 5 times 2, 10. So you get 12/10. Now, if you want to make it into a mixed number, dividing 12 by 10, 10 goes to 12 one time. That's what you have, this digit. And then you have to simplify it. First, it becomes, if we divide both of them by 2, becomes 6/5. So the denominator is 5. The denominator remains the same. And 6 divided by 5, 5 goes to 6 one time with a remainder of 1. So the remainder becomes the numerator. The quotient is 1. So you get 1/5. Okay? You follow me?
Do you mind going over that one just one more time, please?
Okay. You see, we had 4/5. We wanted to divide 4/5 by 2/3. 4/5, I just invert this. You invert this is same as multiply it by 3/2. 4 times 3 is 12. 5 times 2 is 10. So I get 12/10. Now, I simplify it. I divide both the denominator and numerator by the same number, by number 2. This becomes 6, 10 becomes 5. So I have 6/5. That's an improper fraction. If I want to make it into a quotient, into a mixed number, I'm dividing 6 by 5. 5 goes to 6 one time, and the remainder is 1. So your quotient is your integer, the remainder becomes the numerator, and the denominator is the same. Do you need me to show it through the tablet?
I'm getting most of it. I think it's just that last piece that I sort of.
Okay, I think it's easier to see the tablet. Okay, one moment. Let me just remember where we are. Slide 36. Okay, so let me stop here. So, and let's make it new. Okay, so we have. You remember the last area that we came to 12/10. Okay, you followed me all the way to that.
Yep. Yep.
So 12/10. This can be simplified as if I divide both the numerator and denominator by 2, this becomes 6, this becomes 5. All right, but this is an improper fraction. If I want to write it as a mixed number, it means that I have to divide 6 by 5. 5 goes to 6 one time, so I have the denominator remains the same. The quotient becomes your digit, and the remainder becomes your numerator. That's how you get 1/5.
Okay.
All right.
Got it.
Good.
Good to go. I needed to see that one more time too.
Okay. Are you clear now?
Yeah, I'm clear now. I followed all the way to 12/10 and then 6/5, and then I was wondering how once you have that 6/5, how you make the fraction, but you just click.
Okay. You just divide it.
Yep.
And remember that the quotient becomes your digit, and the remainder becomes your numerator. The denominator remains the same.
Yeah, it clicked for me too. I'm glad I'm not the only one. I thought I was the only one with that question. So.
Yeah, I was good to the last part right there, and then once he broke this down, now it's less confusing.
Okay, good. I'm glad. All right, so let's go here. All right. Unfortunately, this thing does that every time I come out. All right. We'll have a break in about 5 minutes. Adding fractions. Again, when you want to add the fraction here, remember those things that we talked about the common denominator and common multiple of denominator comes handy. We want to find the lowest common denominator. To add or subtract two fractions with a common denominator, we add or subtract their numerator. Writing fraction with a common denominator is accomplished with the fundamental law of the rational number. Again, the seeing an example is make it much more easier. Let's say we have two mixed number, we want to add them. 2 1/3 plus 3 3/4. And I draw them here to visualize it. this is 2 1/3, so you have 2 whole row and 1/3 row that are green. 3, you have 3 whole row and 3/4 of a row green. We want to add these two fractions. Don't worry about visualization. That's just for you to help you understand. I don't ask you to draw pictures. So what you do, first you add the digits. 2 plus 3 is 5. Then you want to add the fraction, 1/3 plus 3/4. In order to do that, the rule is this: you need to have the same denominator. And in order to make them the same denominator, the least common denominator, what you do, you take the first fraction, 1/3, you multiply the top and the bottom by this denominator, by 4. 1/3 times 4 times 4 becomes 4/12. And then you take the second fraction, 3/4, and multiply the top and bottom by the denominator of the first fraction, 3/3. So you get 9/12. So I have now 4/12 plus 9/12. I have a common denominator, so I just write that and I just add the numerator. 4 plus 9 becomes 13. And I now do again the same thing that I did. I change that into a mixed number. 13 divided by 12 goes only one time with a remainder of 1. The quotient 1 becomes your digit, remainder becomes the numerator, and the denominator remains the same. Are you guys following me? Do you see that? Yeah. Okay. Now,
I have a quick question. So I see the 4 plus 9 equals 13. Why is 12 plus 12 not 24? It just stays at 12?
What is what? Say it again.
So right there we have 4 plus 9 equals 13. But how come 12 plus 12 isn't 24? It just stays at 12?
No, yeah. Because the whole point is this. We want to make the denominator the same. You make the denominator the same, then you add the numerator. You don't add the denominator.
Okay.
Right? But you cannot add the numerator if the denominator are not the same. So, and in order to do that, you just multiply the first fraction by the denominator of the second one, and the second fraction by the denominator of the first one. And then you make it into a mixed number. So now
I get it. So the goal is to get it to that same denominator.
Exactly.
Denominator. I'm sorry. Okay, I got it.
Exactly. So now I have remember we added 2 plus 3, 5. So I have a 5, and I have this digit here, 1/12. You add the two digits or integers, it is the same as 6 1/12. So that's the answer for addition of these two fractions, 6 1/12. All right? You following me? Any questions?
Yeah, I sort of get you. I see the part. So that one with the 1 and 1/12, you basically on that part you're doing the same thing that we did on that previous.
Yeah, exactly. And then when you come to that, and you had the 5 from the beginning, you had this 2 and 3.
You just add the 5, and it's 6.
So you just add 5 to that 1, becomes 6 1/12.
Yeah. Okay.
All right. So let's keep moving. Irrational number are the decimal number that just continues, like a pi is the famous one, and they are not repeating. Irrational number is a real number whose decimal representation is non-terminating, it doesn't finishes, and non-repeating decimal number. Every non-negative real number A has a unique non-negative square root called, okay, so that's the irrational number. Now we go to the issue of the square root. Has a non-negative square root called the principal square root, which we denote that by that sign, and that little sign is called radical sign. All right. So these are the rules of radical sign. Let's say if I have a radical sign, the root of NA times N radical B, the rule is this: because they have the same principal root, you can just make it into one radical and multiply these two together. And again, if it's a division, again the same. You make them into one radical sign and you divide them together. All right. These are just the rules that you got to memorize, you got to know. When A is greater or equal to 0 and B is not 0. B cannot be 0 because in division we cannot divide by 0. All right. For finding a square root, you just simplify square root. Let's look at these. Oops. Let's look at these and then we take a break. Let's go to page 266. Okay. On page 266, for example, example number 1, it asks you find the square root of 75. Okay, you have radical sign under it 75. 75 is the same as 25 times 3. We can separate them because we have the same square root. Now, 25 is 5 to the power of 2. It comes out of the radical sign, it becomes 5 square root. Maybe it's easier if let me write down the number of the pages and do these things with the tablet. I think that's much more clear. Let me just write it down. 266, 267, 268, and 269. All right. So let's go to the tablet and okay, here. And let me clean this. Okay. And here. It asks you to find the square root of 75 on page 266. Okay. 75. Okay. 75 is the same as 25 times 3. Which is the same as, I can separate these together because they have the same square root. Is the same as the square root of 25 multiplied by a square root of 3. Okay? Now, 25 is 5 to the power of 2. When we don't put a number here, it means it's 2. Okay? Remember that. So 5 to the power of 2 is square root of that. This number gets divided by this square root. 2 divided by 2 is 1. So 5 comes out. That's why you get 5. 5 times radical sign square root of 3. That's your final answer. All right. Are you guys following?
Yep.
Any questions here? Okay. Then let's look at page 267. Example, we look at example 23. Let me clean up here. All right. In example 2, page 267, it says multiply the square root of 2 times square root of 5. Okay, when we have the, again, this means 2, this means 2, so we can write it as 1, 2 times 5, which is equal to square root of 10. And basically, I think that's it. Yeah, we cannot simplify. So that's the answer. If I do, if a square root of 7 times the square root of 7, you see square root of 7 times the square root of 7, this is same as square root of 49, because 7 times 7 is 49. 49 is the same as square root of 7 to, I'm sorry, 7 to power of 2, and this comes out, becomes 7. So that's the final answer. You following me? All right. Let's do example 3, division. 75, square root of 75 divided by square root of 3. 75 divided by square root of 3. Square root of 75 divided by square root of... Again, because they have the same square root, you can just write 175 divided by 3. And that is same as square root of, it says 75 divided by 3 is 25. 25 is same as 5 to power of 2. And 2 divided by 2, so the final answer is 5. All right?
How'd you get the, you went from, okay, the 3
Okay.
times 25. Okay, I got that. But then
Yeah.
the
Okay.
last one.
75 divided by 3 is 25. 25 is the same as 5 times 5, or 5 to power of 2. So we get here, we come here, and we get, we come here, 5 to power of 2. Now, 2 divided by the square root sign is 2 divided by 2 is 1, so 5 comes out.
Okay.
Do you see that?
You say the
You see, I have, do you see how all the way when I get to 25?
okay, yeah, I see. I'm at when you get to the 5 to the 2.
Okay, what is 25? 5 times 5,
5, yes.
which is the same as 5 to power of 2. Okay? Now, this here is not written, but this is 2 also. So we divide this by this number. 2 by 2 is 1. So this is same as 5 to power of 1, or 5.
Okay, I see. Okay.
Right.
I was
So-
missing that 2 that you just put in there.
Sure. Let's go to page 268. Example number 4. Let's first clean this up. It asks us, for example, over there, it asks example number 4, number A, 7 times square root of 2 plus 5 times square root of 2. Okay? Now, these two are the same. So I can factor. So this would be the same as 7 plus 5 is 12. I'm sorry, 12 times square root of 2. You see what I did? You see, square root of, let me maybe choose a different color. Okay, this, and these two are common, so I factor out. I write the square root of 2 times 7 plus 12, 7 plus 5. You following me?
Mm.
So that's the same as 7 plus 5 becomes 12. Where am I get the 12. 12 times square root of 2. Okay? Are you guys clear? If not, let me again go over it.
I'm okay.
Okay. All right. Then, and basically it's the same thing. Let's, let me, 269. Let's do 269, one example over there. Then we take a break. It asks us to divide, for example. Let's do the, did we do, okay, yeah, let's see if we have 15 divided by square root of 6. I find the answer for that. I multiply both the top and the bottom by square root of 6. The answer is this. When I multiply this becomes a square root of 6 times 6, or a square root of 6 to the power of 2. So that comes out, so it becomes 6. Okay, and I'm going to put the equal sign, and the fraction sign, and the fraction sign. 15 times the square root of 6 goes here, and there is actually not much I can do about that, so it just remains there. 15 times the square root of 6, 15 times the square root of 6, but I can simplify this 6 and 15 by 3. That becomes 5, that becomes 2. So the final answer is 5, the square root of 6 over 2. Do you see? Do you follow? Any questions? It's clear.
Yes, just in case the homework or something, we have to refer back to this. Are you going to repost this video?
Oh, yeah. I will do
Okay.
that tomorrow. Yes. All right. So let's take a break for 5 minutes, and then we continue. All right. Good.
Professor.
Yeah.
Did anyone take last week's for the PowerPoint? Assignment 3 for their PowerPoint presentation?
Yeah. The PowerPoint presentation is there, and the video is there too.
No. Did anybody for our PowerPoint? Did anybody take that assignment yet?
Oh, no. Nobody.
Okay, I'd like to take that one.
Which chapter?
Last week.
I'm sorry. What chapter? The chapter from last week.
Yes, I think that was chapter 3.
Okay, fine. That's great. Yes, yes,
That's
yes.
the page
Yeah, you're the first
57
one.
through
So
96.
yeah, that's fine. That's fine.
Okay, thank you.
All right. Okay, see you in about 5 minutes.
Yes.
Uh,
What a sweet person to ask. Of course he can smoke. No.
Are you gonna smoke?
No, I never smoke. I just got a text from Snoop.
Question, is it okay if I smoke at the party? And I have a gift for mom. I want to make sure she gets it. So just let me know if it's okay to smoke at the party. I don't want to be disrespectful. I don't drink too much. I like to smoke. So just let me know if it's okay.
What a sweet person to ask. Of course he can smoke. No.
Are you gonna smoke?
No, I never smoke. I just got a text from Snoop.
Question, is it okay? At the party?
Just pay you, come over and check up on it. I'm gonna let you work up on it. Ladies, let them check up on it. Watch it while you check up on it. Just got a text. I just got a text. Just got a text from Snoop.
Grateful every day.
Just got a text from Snoop.
We got to send him some of them spars.
Hell yeah, he whipped around when he saw my car, pulled me over. I gave him my gun license, my driver's license. He told me he smelled marijuana coming out my car. Pulled me out my car, handcuffed me, called for backup. Backup came, which all officers is not bad. I want to make that statement. So then he came and said, I'm new here. He didn't know what was going on. The officer searched my car, went in my trunk, took my suit, balled it up, and threw it back in the car. This officer needs to be fired. I researched and found out he was fired from Texas City. So somebody is not doing the right background check. You know? And whatever repercussions that comes with it, I'm ready for it. Because needs to be stopped. This man needs to be stopped. I just want to say, he whipped around with
Close your eyes, take a breath, let it flow. Leave the worries, let the sun.
This little kid became a kung fu master at age 6. Even his senior brothers had to listen to him because he knew all 72 Shaolin skills. The abbot saw he was unbeatable, so he sent him away from the temple. He had to find his birth parents with the help of a jade pendant they left behind. But when his family took him back, his parents refused to accept him.
Raised in the countryside really shows he's like a wild kid. Nothing like a child from a wealthy family like ours.
Oh, Dad, now the little brother's back. Does that mean you don't love me anymore?
Don't worry, Zachary. You'll always be our favorite son.
That's the adopted son, Zachary James. He looks exactly like my younger brother previously. He was gay. Interesting. The rival for the family inheritance is just a little brat like this. My deepest respects for him. This is just ridiculous.
Where did he pick up those manners to suck up to Grandma? Mom, Dad, this kid is seriously scheming.
So rude. Just stepped in and left dirty footprints all over the room. Later, you should clean up every last spot. I'm a James by blood. And you, the eldest sister, actually mock me? Are you trying to disgrace the James family? Grandma, I'm home safe. Ancestors be praised. But it was also rushed. I didn't have time to change clothes.
This is James's bloodline. Never forget who you are. It's getting late. Trevor, go take a shower, put on some fresh clothes.
Okay, we can come back. Hello, everybody.
Yes.
Okay. All right. Let's see. Let's go back to our PowerPoint. We did these things. Okay, we are here, number 44. Let me. Okay. Real numbers and their properties. You see this diagram I tried to show you. You have natural number. We talked about that. When we add 0, then we got a set of whole number. Then if we add integers, whether positive or negative, we get the integers. Then the rational number are here, irrational are non-ending, when they have a decimal point, non-ending and non-repeating. That's a picture of real number, our whole number system. Properties of number system. Operation is performed on any two elements of a set, and the result is an element of the set. We say that the set is closed under that proper given operation. We have commutative properties, meaning A plus B is the same as B plus A, or A times B is the same as B times A when A is a real number. We have associative property, meaning A plus B parentheses plus C is the same as A plus parentheses B and C. Meaning, if I add A and B first, then add C is the same as if I add B plus C first and then add A. Or same with multiplication. If I multiply first A and B, then multiply by C is the same as multiplying first B and C and then multiplying the result by A. We have distributive property, meaning if I have an A here in a parentheses, if I have an A here in a parentheses, A can be distributed into this parentheses. A times parentheses B plus C is the same as A times B and A times C. And for any real number A, B, C. Exponent and notation. If you have this number expression 5 to the power of 2, 2 is referred as an exponent, 5 is referred to as a base. And when we have 5, 2, it's read as 5 to the power of 2 or 5 to second power or 5 squared. Let's look at the exponent property on page 282. On page 282, you see on the table 5.4, it talks about the property, the meaning, and example. So it shows if we have b to power of m times b to power of n, it's the same as b to power of m and n. If I have, for example, 9 to power of 6 and 9 to power of 12, the base are the same. So you write the base 9 and you just add the exponents, 6 plus 12. You get 18. The power rule, if I have b to power of m parentheses to power of n, is the same as b to power of n, m times n. An example, if I have 3 to power of 4, parentheses to power of 5 is the same as 3 to power of 4 times 5, or equal to 3 to power of 20. Quotient rule. If I have b to power of m divided by b to power of n, these are from table 5.4 from your textbook, page 282, is the same as you keep the base and you subtract the exponent. It's m minus n. If I have 5 to power of 12, divided by 5 to the power of 4 is the same as 5 to the power of 12 minus 4, or 5 to the power of 8. Look at the, example on page 283, example 1. It has 7 to the power of 0. Any number to the power of 0 is equal to 1. Pi to the power of 0 is 1. Parentheses minus 5 to the power of 0 is 1. What? No matter what. If you have any number to the power of 0 is equal to 1. Notice in C is minus 5 parentheses to the power of 0. The whole thing becomes 1. If the parentheses wasn't there, if it only for the number 5, like the example D, number D, it's minus 5 to the power of 0. 5 becomes 1, but the negative sign remains. All right? Or the quotient rule. You have the same page if you go further down. 4 to the power of 3 divided by 4 to the power of 5 is the same as 4 to the power of 3 minus 5 or 4 to the power of minus 2. And whenever you have a negative exponent, you can make it into a positive one by taking it as a fraction. 4 to the power of minus 2 is the same as 1 divided by 4 to the power of positive 2. Okay, so it has a rule under page 283. b to power of minus m when m is not m is not 0 is the same as 1 over b to power of positive m. All right? Okay, let's move on. So any number to power of any real number divided by to power of 0 is equal to 1. Again, b to power of minus m is the same as 1 divided by b to power of plus m when b is not 0. Product rules. If I have a to power of m times a to power of n, the bases are the same. You just keep the a, add the exponent. Power rule. If I have a to power of m and then parentheses power of n is the same as a to power of m times n. Quotient rule. If I have a to power of m divided by a to power of n is the same as a to power of m minus n. All right? Positive number, you can write, what we have is called scientific notation. You can write a positive number as a scientific notation. When it's scientific notation, that's a scientific notation. This a, when a is any number greater than or equal to 1, less than 10. A to time 10 to power of n, and n is an integer. Okay, changing from scientific notation to decimal notation. Observe now, again, I read this, but let me do an example, would be much more easier. Observe the exponent on the 10. If the exponent is positive, move the decimal point in a number to the right and the number of places as the exponent, and you might have to add 0. If the exponent is negative, move the decimal point in a number to the left, and again, you might need to place 0, and then you put the decimal point. Let's look at, let's see. Okay, let's look at page 285. Example number 3. We have 2.6 times 10 to the power of 7. You see that? That's page 285, example 3. We want to convert this scientific notation to a decimal notation. Exponent is positive, plus 7. So I move the decimal point, you see 2.6, that little point is called the decimal point. I move that to the right, 7 position. So 2.6 times 10 to the power of 7, you move that decimal point 1, 2, 3, 4, 5, 6, 7, becomes 26 with 6 0 in front of it. Why 6 0, not 7? Because one of the 0 has to move, one of the places has to move that decimal point to the right. So that's 1, then 2, 3, 4, 5, 6, 7. You following me?
Yes.
Okay. Now, if the exponent is negative, you move the decimal point to the left. 1.1 times 10 to the power of minus 4. You take that decimal point, you go left. You 1, so it becomes 11, then 2, 3, and 4. So you have 0.00011 because exponent is negative. So if the exponent is positive, you move the decimal point 7 position to the right. If it's negative, you move the decimal point based upon the exponent, actually, whatever the exponent is, in this case, minus 4 position to the left. All right. So now, if you look at page 286, if you look at page 286, we have a number where we have decimal number, we want to convert them to scientific number. for example, we have 4,600,000. Okay. I have, the decimal point is actually, maybe that's easier if I show it with the tablet. No, 1 moment. Okay, you had it. Okay, Robin. Okay, let's go to tablet. Where's my tablet? Okay, here. All right. Let's say you have this number, which is actually, even though you don't see the decimal, but it's a decimal number, 4.4, 4,600,000. 4,600,000. Okay, there is a decimal point here. We don't put it because the number after it is only 0. That's the reason we don't put 0. The decimal point, you don't see it, but there is a decimal point here. If I want to write this as a sign, this is it's a decimal position. If I want to write it as a scientific notation, so I write 4, and then I want to move this decimal point between 4 and 6. I have to move it 1, 2, 3, 4, 5, 6. So 4.6 times 10 to power of positive 6. You see that? See what I did? Let me do then another one. Example number B. It has 0. 4 zeros. 1, 2, 3, 4, 23. Okay. I want to write that as a scientific notation, but notice so I want to move this decimal point between 2.3. So I have 2.3 times 10 to power of. Now, in order to find out what's my exponent, I notice the decimal point is to the left of my digit. So it has to be negative. I need to move this decimal point here. 1, 2, 3, 4, and 5. But it has to be -5 because because this decimal point must move to the left in order to be equal to that number. You follow me? Yeah. Okay, good. All right. So let's move on. Okay. We talked about that. Talked about converting them. We already did that. 2.6. Yeah, we already did that. Computation with scientific notation 2.87, 2.88. All right, let's do example 2. Again, let's go to the tab. Well, yeah, let's go to the tablet. That's easier. Okay, let me clean this. Okay. On page 287, it says computation with scientific notation. And it gives you the general rule. It says if you have A times 10 to power of, let's see, power of n. Okay, oops. Times e to power e times 10 to power of m. What's the rule for that? Is same as a times b times, because the base is the same, 10 to power of n plus m. All right. So it gives you an example. Example number 6. We have 3.4 times 10 to power of 9. 3.4 times 10 to power of 9 times 2 times 10 to power of minus 5. 2 times 10 to power of minus 5. Okay, so I take, following the rule, a times b. So I put the 3.4 times 2 times 10 to power of 9 plus minus b. 9 plus minus b. Minus 5, I'm sorry. Okay, so this is same as 2 times 3.4 is 6.8 times 10 to power of 9 plus minus 5 is 9 minus 5 is it would be 10 to power of 4. That's the final answer. You see how I got that?
Can you work that one more time? I'm
sure, no problem. So we have here, we have an example, 3.4 times 10 to power of 9.
Okay.
Yes. Let's see. 10 to the power of 9. Okay. Times parenthesis 2 to the power of minus 10. So the rule is this. Let me change another color. Take the A and B here is 3.4 and also 2. Take these two numbers, 3.4 times 2, you get this. All right? Then 10 is the base is the same, so I keep the base. The base is 10. 9, the rule is when we have multiplication, we add the exponent. So it's 9 plus minus 5. But 9 plus minus 5 is the same as 9 minus 5, which is 4. All right?
Okay, yeah, okay.
Good. Good. And I think, let me see.
And they simplified even more to equal 68,000, right? 6.8 times 10 to the 4th power. To equal 60.
Okay, that's if you want to, that's a scientific form, but when they write it as 68,000, that is not a scientific notation. That's writing it as a decimal notation.
Okay, so if we're trying to get the scientific notation, it would just be the 6.8 times 10 to the 4th power. Okay, got it.
And if you notice on the same page, the rule, if you have dividing a to power of 10 to power of n times, or dividing by b times 10 to power of n, again, you divide a and b times 10 to power of n minus n. You subtract the exponent. You see that on the bottom of page 287. give you an example. Example 7. I have 8.4 times 10 to the power of minus 7 divided by 4 times 10 to the power of minus 4. You divide first the digits. 8.4 times divided by 4 becomes 2.1, and then divide their exponent. 10 to the power of minus 7 minus minus 4. That minus 4 makes it plus 4. Minus 7 plus 4 makes it minus 3. So the final answer is 2.1 times 10 to the power of minus 3, if you want to write it as a scientific notation. If you want to write it as a decimal notation, because the exponent is negative, you move that decimal point to the left 3 times. You get 0.0021. Okay. All right. And let's go to our PowerPoint again. Okay. Yeah, we did this. Now we have arithmetic and geometric sequences. A sequence in which terms after the first term differs from the preceding one by a constant amount is called arithmetic sequence. If the amount by which each pair of successive term is the difference, the amount of by which each pair of successive term differs is called a common difference. If you look at page 294, you can see an example of that, of a arithmetic sequences. Like, for example, on page 294, if I have, it says, write the first 6 terms of arithmetic sequence with the first term is 6 and common difference is 4. Meaning you start with 6 and then you add 4 to each number. 6, then 10, then 14, 18, 22, 26. So this is an arithmetic sequence with a difference of 4. Now, while we are here, let me also, there's a geometric sequence. Where is that? Okay, if you go to page 297, the geometric sequence is that if they ask you write the first 6 terms of geometric sequence with the first term 6 and a common ratio 1/3, it means the first term is 6, then you multiply each number by 1/3. 6 becomes 2, 2 becomes 2/3, 2/3 becomes 2/9. So that's the difference. I mean, look at it, for example, at the top of page 297. You have 1, then it becomes 5. So I'm multiplying by 5. I'm sorry, turn this off. Multiplying it by 5. Then multiplying it again by 5 becomes 25. Another 5, 125. Another 5 becomes 625. So that's a geometric sequence, and the term that I'm multiplying is 5. The common ratio is 5. The second one, 4 to 8, and 8 to 16, I'm multiplying it by 2. If I have 6 to minus 12, I'm multiplying it by -2. -2, then -12 times -2 becomes plus 24. Plus 24 times -2 becomes -48. It alternates between plus and negative. All right? And that's it. Okay. Any question, guys?
I'm sure I'll have questions, but I'll just review the video and
Okay,
just go.
sure. And if you have any question, feel free to contact me.
Yes.
And, 2 of you chose your chapters. chat, if you could choose your chapter for the PowerPoint, I appreciate. And start working on that PowerPoint so you won't have pressure at the end. All right.
You got my chat right regarding the one I sent you, the chat regarding my selection?
Yeah, I got it.
Okay,
I got
perfect.
it.
Perfect.
All right. Then, guys, good to see you, and I shall see you guys next week.
Okay, thank you.
Okay. Oh, before we go, I forgot. Let's pray. Brother Reuben, could you pray for us?
Yeah, I'll pray. Heavenly Father, thank you, Lord, for this time. Thank you for the study, Lord. Although it can be a bit intimidating for us, Lord. As
Yes, Lord.
It's been a while since we've done this math, Lord. I thank you for just your guidance and for the professor, Lord, for his patience, for the knowledge that you've given to him to share to us, Father. May you help us, Lord, to comprehend and understand what we're trying to learn here, Lord. And I pray for everyone this week as they go along their studies to not get intimidated, Lord, but to trust in you, Father. And we just thank you, Lord, for this time. I pray for everybody's safety throughout the week and for their studies, Lord. And we just thank you for all these things in Jesus' name.
Jesus.
Amen. God bless you all. See you guys next week.
Amen.
Thank you.
Thank you.